Uh, Hello, my name is Iago Toral. I work for Igalia, and I'm going to give a status update on Vulkan on the Raspberry Pi. So very quickly, these are the contents for this presentation. We're going to go through what's the status of the driver today, and then I expect to spend most of the time going through some of the development highlights for this last year, and also go through some pain points that we have in the platform and the driver. And hopefully we'll have some time for a Q&A afterwards. So very quickly, the current status. So right after XDC last year, we gained conformance for Vulkan 1.1. That was in October. And more recently, in July this year, we gained conformance for Vulkan 1.2. Other than the work for getting these, we also implemented quite a few optional extensions in the driver. And one of the interesting changes is the new kernel interface. When we brought up the driver in the beginning, we were reusing the kernel interface that we had for OpenGL, and that, well, didn't quite match what Vulkan expected. So now, thanks to Melissa Wang, we have a new interface that we are using. We have also continued to improve a bit the performance, mostly with compiler backend optimizations, because that's usually where we have most of the bottlenecks in our driver. And also some synchronization improvements that we did. I will go into more details later. A big thing that happened also is thanks to JSON, we are now using the synchronization framework from the Mesa frontend. And then we also got Android support thanks to Roman Strategienko, which is interesting to us because it's not easy for us to find things that we can run on Vulkan on the Raspberry Pi. So I guess having Android support opens up some new opportunities for us. So now going through the development highlights, there were quite a few things that we did on the synchronization aspect. So as I said, the new multi-sync kernel interface was a big thing. Now the downside of this is that we now have to maintain two paths for this, the all single sync interface and the new multi-sync interface. The new multi-sync interface is basically about allowing us to make submissions that can wait on multiple things and signal multiple things at the same time, which is what Vulkan expects. And this is more flexible, is what we want to use going forward. But for the time being, we need to maintain both paths, which is paying for testing specifically. But yeah, hopefully we'll be able to deprecate the old one in the future. As I said, we now use the common synchronization framework in Mesa as well, and this had a number of benefits. One is we gained emulated timeline semaphores, as Jason explained just in his talk, which is great. And also we have some pain points in the driver where we need to do some CPU work during the submissions, which is not nice, and we have some threading stuff going behind the scenes in our key submissions to solve some of that, and now we can kill all of that thanks to this, because there's this new thread submit mode that is supported by the common framework, which is great. Now, as a funny story, we found that after porting to this new framework, with the specific workloads, the performance was reduced significantly, actually, and we traced this down to a bug that we had in our code previously, where we were doing, in certain cases, an active polling on the sync object weight, and that happened to make for much better performance overall. And this is because, and this is not specific to Raspberry Pi, it happens with other platforms as well, the kernel likes to throttle down the CPU when you are waiting for some GPU job to finish, which is, in this case, is not particularly great. And well, it was just a fun story. I know that Jason told me that they had the same issues on Intel, and they were trying to find ways to mitigate this as well. So I guess all the platforms have the same problems. We also reworked our barrier code quite significantly for various reasons, but one of them was, since we are a tiler, when we have barriers that affect geometry stages, we were always unconditionally syncing at the beginning stage. Now we try harder to understand whether synchronization at the beginning stage is actually required, or if we can do that in the render stage, depending on what resources are actually used by the shaders in the beginning stage. Unfortunately, this didn't render significant improvements, but in theory, there may be workloads that get a benefit from that. Another thing we did was we now added a new address format, global address format in here, which is this 2 by 32-bit version, and this was to implement a buffer device address for us. So this is a feature that allows you to have kind of pointers in shaders. And in here, there was the 64-bit and 32-bit global formats, but neither of these were a good match for us. The 64-bit version causes the resulting here to have a few 64-bit instructions, mostly for bitcast conversions and packing and unpacking to and from 64-bit. And since we can't handle any 64-bit on our driver, that was not a great fit for us. And the 32-bit is not valid either because the Vulkan spec makes it very clear that the addresses have to be explicitly 64-bit, so that wouldn't work for us. So we added this, which is basically a way to represent a 64-bit address as a pair of 32-bit values, which is more amenable to 32-bit architectures. Another thing we've been working with is this double buffer mode, which is a way that the hardware has to try to mitigate tile store latency on our platform at the expense of reducing the tile size. So this is beneficial obviously when the tile stores is your bottleneck, but because it reduces tile size, it comes at the expense of additional vertex invocations, which is not great. So you need to have some kind of heuristic to kind of decide when this is going to be beneficial. This is experimental. It's currently running under an environment variable. Well, we have some heuristics in place, which basically track the cost of the geometry side of the pipeline. And well, here are some examples of some workloads that were improved. Things generally that don't have a very demanding vertex processing might be helped by this. Things that require more vertex processing, such as, for example, some Unreal Engine 4 demos that we have around, are generally not something that gets improved with this. So the heuristics that we have in place right now at least are able to differentiate this and disable this optimization for things like that. So we've also been doing some work on the compiler. One is funny, we have spent quite some time in the past trying to aggressively hide latency from memory accesses from shaders, so sampling, UVOs, whatever, because this is usually a bottleneck. So we have been doing this at various levels, scheduling at near, then our own IR after near, we still do things to mitigate this. And then when we meet the assembly, we also try to do that. And what we realized is that we were trying too hard. And when you try too hard and overestimate the latency, what you are doing is possibly delaying the critical path of your shader and incurring an extra performance penalty because of that. So we have to dial back a little bit. And as a result, we observe a small but consistent performance increase across all the workloads that we tested, which is interesting because in the beginning, we never thought we could be running into this. Another thing we changed is that in the past, in the last presentation I did here last year, I mentioned we had done quite a bit of work on the compiler to have multiple compiler strategies trying to optimize shaders so that we don't have spilling if possible. And one of the pain points there was that if you have spilling, that is a very, very slow process because we were rebuilding the interference graph every time. So now we don't do that anymore, which makes this a lot faster. We do recompute liveness though, because if you don't, then the quality of your spilling is decreased very significantly. But nowadays we can run, what we can do is with each of the compiler strategies that we have, we can like run it fully with all the spills and fills, and then at the end we can choose the one that is the fastest for our platform. We don't have to stop the process as soon as we see a spill because we can take the compile times. And now some pain points that we still have. One of them is, I think Jason mentioned this in his talk yesterday, we have some cases in our driver where when we submit a common buffer, some things need a CPU intervention. And this is very annoying. Vulkan assumes that when you submit something in a common buffer, it's going to run completely on the GPU, and it's not the case right now for us. This is an annoying thing, really. So the capacity in the synchronization framework to do thread submits helps a bit with this, but it's not something that we really like. We would really like to do everything on the GPU if possible. This is also one of the reasons we can do syncfd exports, because syncfd exports require that when you submit something, you can immediately export the fence, the DMA fence that is behind the sync object. And in our case, that may not happen if we have to wait on something to execute on the CPU. I hope we can find ways to get rid of this. For some things, it may be easy. For others, I'm not so sure. So maybe I can talk to Jason or someone else to see what options we have for some of this. Another thing is FP16. So ideally, we want to have this. But the way I would like to have this is you would want to have faster FP16 instructions, but we don't. What we get is the capacity to emit 2 of these at the same time, but with very special constraints on register allocation. You need to have your operands on the same registers, on the upper, lower 16 bits of them, and the results the same. So you need to kind of mix and match your operands and registers in ways that make this work, which in practice I think is very difficult to exploit optimally. So we have decided not to do anything about this for now. We do implement the 16-bit storage extension, but then we just convert to 32-bit internally. So that's all we are doing for now. And then sync. So CMake didn't mention B3DB as one of the drivers. Yeah, that was supported, and that's a pity, especially because we used to support it in the past. Sync was one of the first tools we had to test the driver. Unfortunately, as Sync continued to evolve, it also started to require more features from the underlying implementations. And one of these is a scalar block layout, which I think is still a thing, right? No.
The only difference is at one point it did explicitly.
Oh, okay. So this is something that we cannot implement optimally on our platform. But I think it's a pity that we cannot support sync just because of that. So maybe we can try to add some lowerings for this that we can implement suboptimally, if only to at least get the possibility to continue testing the driver through sync, maybe under an environment variable or something like that. And yeah, I think that's it. Now, if there are any questions.
There's a question for Rachel.
If the driver knows that the process is 32-bit, can the driver optimize away 64-bit address generation to be more optimal?
Sorry.
If the driver knows that the process is 32-bit, can the driver optimize away 64-bit address generation to be more optimal?
Okay, I guess this is talking about the buffer device address stuff. So it doesn't really matter if the process is 32-bit or 64-bit. So the Vulkan spec states that the addresses have to be 64-bit anyway. And our GPU, independently of whether we are in a 64-bit or 32-bit environment, it only understands 32 bits anyway of addresses, so we cannot use anything larger than that. So that's what we get. Yeah, if you have any thoughts for that.
Not immediately, other than that, it seems to be a hack.
Yeah.
So we should maybe avoid that.
Should I repeat? So yeah, Jason was saying that basically the issue that we have with FP16 is a pain point that's shared by almost everyone. So that maybe we should work together to find a solution for that. Oh, woof, summarizing all that. I think I might as well pass the the microphone to Elisa if she wants to repeat that. So the question is, how are we testing the driver, like with traces, basically? Yes, so we have a few samples from Unreal Engine 4, and then from those we have a few traces that we use mostly for performance, for tracking performance changes when we do optimization on the shader compiler, and that's basically what we do with that. Then we have in CI we have some traces from these Unreal Engine samples as well that we might test for regressions every now and then. Okay, thank you.